Okay, so guys, now we're going to talk about geometric progressions, okay, also called geometric sequences. And I'm going to erase this and rewrite it afterwards. Okay, what's a geometric progression or a geometric sequence? This is easy. This is the general form of any geometric progression or sequence. Here, okay, this is a sub n equals a sub 1 times r raised to the power of n minus 1. Now, instead of adding a number all the time, we are going to multiply. Okay, we will be multiplying that number by a constant. Okay, so each term is the previous one, but multiplied by a specific number. That number is r, which is called the ratio. Okay. Okay. So the typical. Okay. It's a discrete version. We'll write this afterwards. Okay. So the typical example of this, for instance, is the case of the coronavirus spread. That's a very, very illustrative case of a geometric sequence. Okay. So what happens with the coronavirus spread? On day one, we have the patient zero. So this is one person who is infected with the virus. Okay. Then this person, on day two, this person infects two people. Okay. These two people are going to infect on day three. This person is going to infect two more people. This other person is going to infect two more people. Okay, and so on. This guy here will infect two more. This guy here will infect two more, and so on. Okay, so how can we express this by using this? How are we going to express this by using geometric sequences? Okay, we are going to take the geometric sequence formula, the general term, which looks like this. And we are going to replace the values. So the original value, a sub 1, is 1. Because on the first day, I have only one guy who is infected with the virus. So a sub 1 is 1, this guy. How many people does he infect per day? Or how many people does each infected person infect per day? 2. Okay, guys, I'm recording myself, so please, any questions at the end of the explanation? Okay, so 1 times 2 raised to the power of n minus 1. Here's the variable n minus 1. Okay, so this is the general term for this case. Good. Then, if I want to find a sub 1, the variable takes the value 1. 1 minus 1 is 0. You know that any number raised to the power of 0 equals 1. So 1 times 1 equals 1. So the first term of the sequence is indeed 1. Let's find a sub 3. A sub 3, the variable takes the value 3. So this is 1. This is 1 times 2 raised to the power of 3 minus 1, which is 2. Okay, so this is going to be 4. On day 3, there are 4 new people infected. Okay, if we keep computing this, we will be getting these values. Okay, so Let's say I want to compute day 5. So on day 5, I'm going to get 1 times 2 raised to the power of 4. So this is 16. Okay, so on the 5th day, 1, 2, 3, 4, 5. On the 5th day, I have 16 new infected people. As you might see here, the sequence gives me the new infected people per day. Okay, if I want to compute the total amount of people infected, I would need to use the series. Okay, but here I'm using the sequence. And right before I stop recording, what I want you to see here is that, okay, this sequence on day 1, I have 1 person infected. On day 2, I have 2 new people infected. On day 3, I have 4 new people. On day 4, I have 8. On day 5, I have 16. On day 6, I have 32. Okay, so this, which kind of pattern do we see here? This is exponential growth. Okay, so here, if I write this, okay, 1 times 2 raised to the power of x minus 1. Okay, this is an exponential function. Okay, this green line, and the points are a geometric sequence. So here we can say, this is which was written before here, the geometric progression or geometric sequence, it's the discrete version of the exponential function. Okay, so this is a geometric sequence, this is an exponential function. Okay, so geometric sequences describe situations of exponential growth or exponential decay. I'm going to stop recording here